Thank you very much. So let's talk a little about infrastructure. When you have an ML or a general AI algorithm, you need to take it from research into production, and there is a lot of infrastructure involved in that, a lot of tools that are offering assistance today. And one of them is lakeFS, our open source project. And we're actually coming from the world of infrastructure and data and not necessarily from ML, but we have learned from users that being able to reproduce things is extremely important for ML pipelines. And this is why 40% of our users actually come from the ML domain. Let me tell you a little about lakeFS and not at all about fundraising. Boring. So usually when you do have large amounts of data, and some of it is semi-structured or completely unstructured, for example, videos, pictures, brain MRIs or whatever, you start keeping it in an object storage, which is a very cost-effective way of saving data. And what you can see here is the set of technologies that usually work around an object storage. If the term doesn't mean anything to you, I'm talking about storages like S3 on AWS or Azure Blob. Those allow you to actually save files in any format that you want. So you don't have any commitment to a specific format. It doesn't have to be a table. It's not a database, so there's nothing to think about before saving the data. And on the left-hand side, you can see the set of technologies that are usually assisting in saving data into such a lake. On the bottom, you can see the Hadoop ecosystem that helps you run, among other things, ML algorithms, for example, using Spark. You can then use all the famous Python libraries to run the algorithms. On the right-hand side, you can see data exploration tools such as Jupyter, that is very commonly used with AI and ML. Visualization tools, more relevant to analytics. And on top, the analytics databases that all have their deep storage within an object storage. So if you're using Snowflake, for example, do know you are also using S3 or whatever object storage your cloud providers allow. So this is the architecture that we were looking at, and it's the architecture that we had at SimilarWeb while running just thousands of jobs of ETLs and learning algorithms. And it's really very good. It's very cost effective. Throughput is amazing. But when it comes to experimentation, that is a very important part of the work of developing an algorithm, it becomes hard to work. It's hard to work because if you want to get isolation, so to work on a copy of the data that is only yours, then you need to copy the data. And those are not small data sets, as you all know. So you would have to copy maybe hundreds of terabytes. That would mean tens of millions or maybe hundreds of millions of files. And those actions tend to fail. Anything you want to do, basically, you would have to copy data. So if you want to compare two things, you would have to have two copies of the data and compare between them once you're done writing, or you would have to very carefully control the paths. And it's very hard, therefore, to reproduce things. For the same reason, it's difficult to enforce best practices. If you want to make sure that the format that you are using is exactly what you're expecting, or the metadata that you're saving with the data is exactly what you expect, there is no process or structured way of doing that. And that results in, more often than not, in low quality of data that those processes produce, or very, very hard manual work of trying to reproduce things, trying to understand where problems came from, because while you're working, the data is constantly changing under your hands. So anyone working with such an architecture is probably familiar with those problems. And when we had a little tragedy, I won't bore you with the details since we don't have much time. I remember myself, while cursing, thinking to myself, why can't I just manage this data the way I manage my code? There are so many good practices. I have a version control system. that I can use. If something's wrong, I can always revert. If I need to go back to a certain version of the code, it's always there under the commit ID with the relevant metadata. If someone did something wrong, I can use git blame and find out, it's not git blame, by the way. It used to be SVN blame, though, and find out who was that person who did the mistake, and then they could help me maybe fix it, and so on and so on. None of that exists in data. So we're basically managing petabytes of data in a shared folder. And then Oz, my co-founder, said, okay, we can do that. We can create something that behaves like Git over an object storage. And that's how lakeFS was born, and it is an atomic version data lake on top of an object storage. And it is also a very, very cute logo, moving its ears there. That's an axolotl, by the way. So what does lakeFS do? It behaves like a wrapper to your object storage. So we don't save the data. The data is still saved on S3 or Google Cloud Storage or Azure Blob, or if you're on-prem, probably Min.io. We're not moving the data. We're just providing a wrapper that allows you actually to access the data from all the applications you access the data through today. But you can have additional commands that you can use that are very similar to Git. So on this slide, you can see on the left-hand side, we have all the regular API calls that you would use to call the data, either get or put or list. And then on the right-hand side, you can add to that the ability to branch the data, to commit data, and to merge data from a branch to your main production data. And in the middle, there is, of course, a versioning engine that is proprietary to lakeFS, and you can look at it and read all about it in our documentation. Since it's open source, then the entire brain of the system is open to everyone. How is it used? So at the end of the day, for you as a user, once this is configured, the only difference you have from whatever it is you were doing earlier is that you need to mention what branch you're accessing when you're accessing data. Instead of just accessing a bucket in S3, you now need to mention you are accessing main. Main would usually be your production data branch. But you could also access my branch or experiment one branch, and then you work in isolation on your own branch. Then all the applications that you know and use, and this is a partial list, know how to work with lakeFS kind of out of the box. The integrations are very, very simple. And as you can see, it exists for most of the relevant tools today. So how does it really help us work now that we have lakeFS in there and it's between the data and the application that you are using? Now, if you want to experiment, you can just go into the main branch, which now holds production data, and open a branch. When you do that, you have experimentation. You have isolation because this is your own branch of the data, and you can play there and do whatever you want. No one else will see. You can now debug a problem. There's now a problem in production with the data. Without accessing production, you can just open a branch and debug the problem. And you can collaborate over a snapshot of the data that is within a branch. So let's say we want to develop an algorithm together and we want all to use the same data set, but our data, it keeps on coming in from all its sources. We want to make sure we're all working on the data set, the same data set. Instead of copying it to the side, we can now open a branch and collaborate on this branch, develop there together, just like you do with code in Git. So this is just a small illustration to make it clear. You have the main branch. Actually, when we say you have a main branch, what we mean is we created a set of pointers that point to the data that you consider production data. Once you open a branch, here you have experiment 1 and experiment 2, two different branches open from the same time in main. Then what we do is actually create those pointers again for those two branches. So at the beginning, at the opening point, all three metadata sets look exactly the same. They all point to the data in main. But now you'll do an experiment on experiment 1 and a different experiment on experiment 2. You'll probably be deleting data, writing new data, and this is where those pointers are going to start changing. Main will stay the same. It will show the exact same data it showed before, but your experimentation are going to look differently, and hence the branches would look different from one another. And if you want, you can easily compare them through lakeFS and see the list of files that actually changed once you did the experiments. So you understand that from a storage perspective, this is very cost effective. We are hardly copying anything. We are doing metadata operations. Allow me to skip the code examples. This would be available for you later, or you can see it in our documentation. Now, what happens during deployment? So you want to deploy data to production. That data could be an ML model, right? This is actually, at the end of the day, a data file or a configuration file that provides the parameters. So you want to have version control. So you want to be able to ingest new data to an isolated branch and test it before you push it to production. And you want to be able to test not only new coming data, but also data that was created during production. So this actually is presented very well in this slide. So instead of working on main and just pushing and pulling things from the actual production data set, you want to ingest data into a branch called new data. When you ingest the data into the branch, it is not exposed to the users who are reading stuff from main. So if your production inference is reading from main the new model, it would not be seen because it was just written to new data. Then you can run a set of tests. Here, the tests you can see are actually schema validation, but you can run much deeper tests and use pre-merge hooks to make sure that only if the tests passed, the data is merged into main and then can be used, launched, whatever, into your production users. This way you protect your main from exposure to wrong data, problems with the data, and actually create sort of a CI or a CD for your data sets. Again, a code example that I would skip this time with Pyro. And then we have continuous data deployment and actually the behavior of data in production. So yeah, the headline here should have been production. So why is lakeFS so powerful in production? First and foremost, because you can roll back. Once you have the concept of merging new data into main, as we saw here, then you have an ID for this merge that happened. And then you have an ID for the next merge. And if one of them, for some reason, was faulty, tests don't really cover everything, and you found you have a problem in production data, you can then revert. And by reverting, you revert to a consistent stage of your data lake. If you want to troubleshoot, if there is a problem, I think I said that at the beginning of the talk, you can just open a branch from production, and now while production keeps on advancing, you can work on an isolated data set, an isolated snapshot frozen in time, and debug the problem without losing the trail of what actually happened. You have it kept on the side for as long as you need it. And cross-collection consistency, if you want to synchronize several data sets and commit them together so that later jobs that are running or later algorithms that are running would read the consistent data sets, then you can do that. So I'll explain what's going on here and then I'll be done. Here you can see a stream of data that comes from sales, and then the leads daily job that runs. But at the end of the day, you want all those 3 data sets to be consistent, to talk about the same set of users at the same time frame, and probably additional requirements that we have for consistency. Then by using different branches of lakeFS and then committing it together, you get that consistent snapshot that you can later on revert to. So this is really a very, very short introduction to what lakeFS can do for you, and I hope it was helpful. Feel free to ask me questions on our Slack channel that you have a link to here, or you can just go into docs.lakefs.io and get everything there, including the ability to join the Slack and ask me questions. Thank you very much.
Thank you, Einat. Very impressive open source project.